Hi there, welcome to this lecture series on matrix algebra. This is lecture 19, part 2. The topic is determinant, and this is actually the second lecture on the topic. In this lecture, we focus our attention on geometric meanings of a determinant in various situations. Okay, let's get started. Let's consider the matrix multiplication as a linear transformation. In the two-dimensional case, consider a matrix A, which is a 2 by 2 matrix, and it will give us a linear transformation from R2 to R2, defined as follows. The transformation will transform X into Y, both in R2, where the Y is defined as a linear transformation of X, f of X, such that Y equals A times X. So a 2 by 2 matrix times a vector of length 2 gives you another vector of length 2. Now let's consider the A matrix in this form, where we write V1 and V2 as the two column vectors. And then we know that these two vectors, V1 and V2, would be the linear transformation of the unit vector, which we call E1 and E2. So E1 will be 1, 0, which is here, and E2 is 0, 1, which will be the unit vector here. And then V1 will be A times E1, let's say assuming V1 like that. And then V2 is A times E2. Let's say V2 is like this. So this linear transformation maps a unit vector E1 into a vector V1 and the vector E2 into another vector E2. Then if you consider this unit square in the standard Cartesian coordinate, let's call it Q, then the image of this square, meaning the area occupied by f of q, the linear transformation of q, which is just the y is a times x. Okay, this will also become a parallelogram, and the sides of it will be exactly the v1 and the v2. And then one important property of this transformation, if we treat it as a linear transformation of an area into another area, is that this area of the transformed area f of q divided by the area q of the original q here. If you consider this as a little square and this is a parallelogram, then this area is just 1. Then we'll just get area of f of q. And then the area of f of q we know is computed as the determinant of A. So actually this is a more general property regarding area. You don't have to start with a unit square. It's more general in the sense that any area here in the x1, x2 coordinate after the transformation becomes f of s here, and then the ratio between these two areas is always the determinant of A. Okay, so area of f of s, the transformed area, over the area of S, the original area here, the ratio is absolute value of the determinant of A. So treating the multiplication as a linear transformation, we see that this number that we call determinant is exactly measures the ratio of how the area changes. Now let's take an example. Let's consider a linear transformation like this, where we give a matrix A, which is 2, 1, 1, 3. And then we want to find the image of the unit disk S, which is x1 square plus x2 square less than 1. So that is like a unit circle, an interior of the unit circle. And we want to compute the area of the image of that. And we can use what we have just discovered, and that is the area of the transformed, the image would be the area of the original region S times the absolute value of the determinant. So we can compute the determinant, which is 2 times 3 minus 1, so we get 5, and the area of a unit circle is pi. So this image here, which probably look something like this, and that area would be 5 times pi. Now let's dig a little bit deeper, try to find an expression for the image f of s. We can use the relation y equals ax, and then we can also write now x would be A inverse times y. Here the A matrix is given, and then we can do a calculation to find the inverse, because the determinant is 5, so this is invertible. Let's say we carry out the calculation and we find the inverse of A, which is here. Okay, so now let's find an expression. Let's find the expression of x as a function of y, the vector x as a function of the vector of y. Okay, so from here we know that it is A inverse times y. Let's put in A inverse here, and let's write out the component y1 and y2, and then we can do this multiplication and vector matrix multiplied by vector, and we'll get a vector. If you carry out, you get this. So that means x1 is this, which we write down here, and then x2 is this. So now we are ready to write out an expression for the image of S that will be all the point y such that A inverse times y, meaning the x, where this came from, the x will lie in S. And then we just computed here that the x1 and x2 can be expressed as y1, y2. So this then becomes y1, y2, and then here would be the x1 square plus x2 square is less than equal to 1. So let's put in x1 is here, so x1 square plus this will be x2 square, that's x2 here, that shall be less than equal to 1. Okay, and one can open up this and combine the like terms, and in the end you will get 3 terms. One is y square, and then y1 square, and the other is y2 square, and the third is y1 times y2. So you collect all these terms together, you have that, and less equal than 5. That's because to get rid of the denominator, we multiplied by 5 to get rid of one of the 5 factors, and that will be the inequality satisfied by y1 and y2. Next, we look at composition of linear maps. Consider the composition of 2 linear maps. Let's say f and g. F maps from x to y, where y is A times x. And then g maps from y to z, where z is B times y. So A and B are 2 matrices. And then you can combine them. You will know that z now equals B times y, and if I put in the expression for y as A times x, then I have a relationship between z and x. So z will be B times A times x. So here is just a visual understanding. So you have an S, and then you do a linear mapping F, which is this one here, and then you reach this image F of S, which we call is Y, and then take this Y and we do a second linear mapping with G. Then we go to this coordinate Z, and which, for example, take this shape, that is the composition G of F of S. So the question now we want to ask is, now what happens to the areas? This area and this area and this area, how they relate to each other. Okay, so from what we have studied, we know that this map F would expand this area, let's say, assuming determinant is bigger than 1 in absolute value. So it expands it, and it expands it by a factor of determinant of A in absolute value. And then similarly, from here to here, the map G does a similar thing. It also expands the area by a factor of the determinant of the B, the associated matrix to it. Okay. And then the composition from X to Z, going through 2 rounds of linear transformation, would be expanding the area by a factor of the product of these two. So the determinant of B in absolute value times the determinant of A. And then from the property of the determinant, we know that that exactly equals the determinant of the matrix B times A. Okay, we can consider an example. Let's say we have the transformation F, which is associated with this matrix here. So Y will be this matrix times X. And then the transformation G of Y is this one. You have a matrix. Z will be this matrix times Y. We can verify the area by considering a unit square in R2 for X1 and X2. And then we want to compute the area of F of Q, and then the area of the composition G of F of Q. And we want to check if the area are magnified by a factor as we stated before, that is the determinant of the matrix A and the determinant of the matrix B for the linear transformation of the first one and the second one, and the determinant of C, which is B times A, that will be the composition of the transformation F of G of F of Q. Okay, so we can work out the product now, B times A, because we'll need that. And you work out the B times A, it's a 2 by 2 times a 2 by 2, and you get a 2 by 2. So just as a note, you can write in this relation, Y is A times X, and Z would be B times Y. And if you put it in A times X for Y, you get this relation. And then you can write C to be B times A, and then you can write it as C times X. Now let's check details of these linear transformation. So first, the F, that is from X to A times X, where A is this matrix. Then we know that the vector E1 is mapped to the first column vector, 3, 2. So this one is mapped to this one, which is 3 and 2. And the second vector, E2, second unit vector, is then mapped to the second column, that is -1, 0. So this E2 is mapped to this V2. Okay, so therefore this little unit square is being mapped to this parallelogram. And now we can compute the determinant of A, which we find is 2, so it's 0 minus -2. Since that's 2, that means that the map, X mapped to Fx equal Ax, would enlarge this area here by a factor of 2. So the area of the image of S would be 2 times the area of S. And for all S in R2, any shape here. So for the case of a unit vector, so have a unit square here, and one can easily verify this parallelogram will have area twice as that one. Now the second linear map, G, which maps Y to B times Y, and B is this matrix. We can go through a similar argument. So the vector E1, the first unit vector, is being mapped to the first column, which is 1, 1. So the W1 is here. And then the second unit vector, E2, here will be mapped to the second column. That's 2, negative 1, which is here. So a little unit square here now is mapped into a parallelogram like this over here. So here you see that the orientation is being flipped. So from E1 to E2 is counterclockwise, but from W1 to W2 is clockwise. Okay, so we can take this B matrix and compute the determinant, and we found out it's negative 3. So that taking absolute value of that, and then you get 3. So that means the area from this coordinate y1, y2 after the linear transformation will be enlarged by a factor of 3. Okay, so one comment here would be the minus sign in the determinant is due to the fact that the orientation is reversed. So this one is counterclockwise, and then afterwards it becomes clockwise. Now let's look at the composed map from X to Z directly, where it's a B times A times X, and then B times A. We call this matrix C. We computed is this one. So we go through the similar argument, and looking at E1 is now being mapped to the first column, which is 7, 1. So it's U1 is right here. And then the second vector, 0, 1, E2 here, is being mapped to the second column. So negative 1, 1, which will be U2 here. So this unit square is being mapped to this parallelogram in the Z coordinate. Okay, so we can now compute the determinant for this matrix C, which is B times A, which is here. And you can compute it's 7 times 1 minus negative 1 times 1. You get negative 6, or you can also compute this as determinant of C is determinant of B times determinant of A, which gives you the same number. Okay, so the composed map from X to G of F of X, which is C of X, it will enlarge the area by a factor of 6, which is the absolute value of the determinant. So we can conclude the area of the image of the composed map is 6 times the area of the original region here. Okay, so again, a note on the minus sign in the determinant. We know that it's caused by switching the orientation. So here again from E1 to E2 is counterclockwise, but then here from U1 to U2 is clockwise. Okay, so we've come to the end of this lecture on determinant, the second lecture we have. But we still have a lot more to say on the topic, which will still be the subject of the next lecture. Okay, so I hope you enjoyed today's lecture, and I'll see you next time.